Okay, so before we can understand how to construct a decision tree, we need to understand three concepts: entropy, information gain, and Gini impurity. I'll explain all these concepts one by one, and to explain them, I take this example of this data set that you see right here. Okay. Uh, yeah. And this will be and I've taken this data set from the lecture slides of University of Rhode Island. So you can just go there and you can have a look at this at the slides if you want to. So first up, we have this concept of entropy. All right. So what is entropy? Let's say I have a data set, okay, and I want to make a decision tree on this data set. And my random variable, which is basically my dependent variable, or in this case, whether it's the variable that I'm trying to classify, whether it's in this case, if you look at this data set, the variable that I'm trying to classify is whether I can play tennis, given that these are my features: outlook, temperature, humidity, and wind. Okay. I want to classify if given these four features, I want to classify whether I can play tennis or not. So I have my output variables as y1, y2. Let's say I have my output variables as yk. In this case, I have only two output variables, yes or no. But in general, if I have k output variables, then the entropy of my output variable hy is given with this following formula: negative I equals 1 to k, where k is the number of class labels that I have. In this case, k equals 2. Okay, k equals 2 over here. But if you have a multi-class classification problem, then the entropy of the variable, the output variable y, is given by summation I equals 1 to k, probability of yi log to the base b, probability of yi. Okay, now what is b? B is either 2 or e. Okay, if it's e, then it's called the natural log. So b is either 2 or e, but this is the formula for entropy. Okay, now think of entropy as a measure of randomness. Okay, that's what you should remember. If it'll help you understand what entropy is. Entropy is basically a measure of randomness, right? So, yeah, so now if you look at this data set and you want to calculate what the entropy is, so look, in this data set, I have h of y as, if I take that formula, I have it as negative p of yi, where yi is equal to yes. So I'll consider probability of y equal to yes, which is, I think it's the number of yes over here. Look, the total number of data points is 14, and the number of yes over here is 9. So probability of yi, which is minus 9 by 14, log to the base 2, 9 by 14, minus the probability of no, okay? 5 by 14, log to the base 2 of 5 by 14, right? That's your entropy. So if you calculate this, you get the value of 0.94 as your value of entropy, okay? So that's how you calculate the entropy of your output variable or your dependent variable for a data set. Now let's look at some properties of entropy, all right? So let me just show you some properties of entropy. Properties of entropy. To try and better understand what is the significance of entropy, right? I mean, this is a formula and it's easy to calculate what the entropy of this entire data set is, right? It's easy to calculate that. But what does entropy actually mean? So I'll do a case by case study. Case 1. Let's say my data set has 99% positive variables, okay, y plus, and it has 1% negative variables, y minus. Okay, so if I take the entropy over here, I'll have the entropy as minus 0.99 log to the base 2 0.99 minus 0.01 log to the base 2 0.01, correct? And this comes out to be 0.0801. Okay, now let's look at case 2. If I have my data set where I have equal number of data points, 50% positive points and 50% negative points. Okay, in this case, my entropy comes out to be zero point 0.5 log to the base 2, zero point 0.5 minus zero point 0.5 log to the base 2, zero point 0.5. In this case, my entropy comes out to be 1. Okay, this is where I have maximum entropy. If my data set is perfectly balanced, I'll have maximum entropy. And case 3 is where let's say that I don't have one class at all. Let's say I have only 100% positive classes and I have 0% negative classes. In this case, my entropy is 1 log to the base 2, 1 minus 0 log to the base 2, 0, which is 0. In this case, it's minimum. Okay. So if you look at this, entropy basically varies with how balanced or imbalanced your data set is. It's minimum when your data set is extremely imbalanced or it's highly skewed in one towards one data point. Sorry, not towards one data point. It's highly skewed towards one class label, and it's maximum when it's equally balanced. Okay, when it's not skewed towards any class balance. So if I have to plot entropy, I would, this is what the plot of entropy would look like. Okay. Let's say this is the probability value, or the probability of the number of classes that I have in my data set. And on the y-axis, I have my entropy. Okay. So my plot actually varies like this. The plot for my entropy is something like this. Where this is, well, look, if the probability of observing a class label in my dataset is zero point 0.5, then this is where I have the maximum value of 1. Okay. Over here, it's 1, and over here, it's 0. This is what the plot of my entropy looks like. Okay. So just to sum it up, if classes are equally probable, if classes are equiprobable, I don't know if that's a word or not, but then the entropy is maximal. Okay. Otherwise, if they're highly skewed towards one class label, then my entropy is minimal, right? So this is entropy, and in the next video we'll study what information gain is.